This is a brief lesson on bond polarity, specifically looking at covalent bonds, polar and nonpolar covalent bonds, and percent of ionic character. First, electronegativity was left for Chapter 8 by Zumdahl. Electronegativity is the pull and, in your packet, the pull of an atom for electrons in a chemical bond. All the other periodic trends looked at the atom all on its own, atomic size, the energy to remove an electron, the energy released when an electron was added. Looking at an element all on its own. Here's the interaction of an element with another element. The pull an atom has for electrons in a bond. It's a tug of war. It is a tug of war when they are sharing electrons. Because even though they're both winning, they're going to try to hog them. Atomic size governs electronegativity. If we have a larger element sharing with a smaller element, the smaller element will actually win because the electrons it is pulling for are closer to its nuclei than the larger one. As we go down a column, we know that our atoms get larger. So the strength, the ability of them to pull electrons toward their nucleus actually decreases. As we go left to right and get much smaller, the electronegativities increase because our smaller atoms can more efficiently pull for the electrons. If you think of a tug of war, the smaller elements can hold on with two hands to the rope, where the larger atoms are kind of just barely holding on with their tippy fingers. So they just can't efficiently pull, hence have lower electronegativities. Now, on this table, the noble gases have been completely left off. They are assigned values of 0 because they have no need to even play tug of war. They already have their 8. Now, we can force the larger noble gases to react, and then we can measure an electronegativity. But in general, we say that the noble gases have electronegativity values of 0. Fluorine, then, being the smallest minus the noble gases, has the greatest electronegativity, being our smallest element. We assign him a value of 4. Then everybody else is assigned a value in comparison to him. Now the table that we have, that I've placed in your packet, I know these are kind of relative. We're so used to seeing fluorine as 4, and this is 3.980, but it still teaches us what we need to see. So when I pull values from here, I'll actually round to the 10th. It's very nice. This table that I have, I was able to find them to the 100th. All right. So even though in covalent bonding we say that they're sharing electrons, it's usually never equal sharing. The only true sharing will occur between an element bonded with itself. Only then, for example, in the case of fluorine with fluorine, do they have equal strength at pulling electrons. He's going to pull, they're of equal strength, no one will win. So the electrons will spend an equal amount of time on either side of this bond. We say then that this kind of a bond is non-polar, where there is equal sharing of electrons. In the case, however, of carbon bonded to fluorine, carbon being 4.0, carbon being 2.6, we can clearly see, and because of size, he will hog the electrons. So the electrons are going to spend more of their time around fluorine and less around carbon, more here and less around here. It's not like an ionic bond where carbon has given the electron. The electrons are just being hogged and are just, fluorine is being extraordinarily greedy. Since the electrons are spending more time around fluorine, this side of the bond gets a partial negative charge. not a full negative, like chloride when it gains an electron. This is a partial charge. It looks like a musical note, doesn't it? And because this is without the majority of the electrons, this is going to, by default, get a positive. So we have an imbalance of charge. This is called a polar covalent bond, where there's unequal sharing of electrons. So, do we only have nonpolar covalent bonds when they are the same element? The general rule of thumb is this. If you look at the electronegativity between your elements in a bond, if the electronegativity difference, subtracting between the two, is between 0 up to 0.3, then we say it's a nonpolar covalent bond. If it is equal to 0.3 up to 1.7 in the electronegativity difference, we say it's polar covalent. Beyond that, the difference usually is yielding an ionic bond. It's such a great electronegativity difference that there will be a full giving and taking of an electron. If we look at 3 different bonds, boron to fluorine, iron to oxygen, carbon to oxygen, hydrogen to phosphorus, the electronegativity difference between these two, boron is 2.0, fluorine is 4.0, the difference being 2.0. And we can do absolute value. Iron is 1.8, oxygen 3.4. We get a difference of 1.6. Carbon to oxygen, 2.6, 3.4. We get 0.8. Hydrogen to phosphorus. Hydrogen, sorry that I didn't realize that wasn't being shown. Hydrogen is 2.2, and look, phosphorus is 2.2. This is a difference of 0. This, amongst all the examples, is our only nonpolar covalent. 0.8 would be polar covalent. Now what about these guys? Now this technically falls in the realm of being polar covalent. However, it's a metal and a nonmetal. Composition trumps electronegativity difference. Nonmetal, we know it's covalent bond. Nonmetal, covalent bond. Metal, nonmetal, ionic. Even though this is, again, the electronegativity difference would show us polar covalent, this is ionic based upon composition. Now here, nonmetal, covalent, the electronegativity difference would put us in the realm of ionic. However, it's covalent. It is going to be about as polar covalent can get. In fact, if we had to rank these in percent of ionic character, from least to greatest, meaning which is the least ionic in nature or the most covalent, that would be the hydrogen-phosphorus bond. Next, the carbon-oxygen. Next, even though this is very, very polar covalent in the case of almost being ionic, we put this guy next, and then your iron and your oxygen. Percent of ionic character is increasing in this direction, but percent of covalent character is increasing in this direction. This is a graphic that conveys electronegativity difference, just what I had written. Electronegativity difference, where we classify up to 0.3. So if it's 0.3, it would be polar covalent. 1.7, you're going to rule it based upon composition. If it's polar covalent, nonmetal, ionic, metal, nonmetal. Percent of ionic character. And I like this because, as we see, as our difference in electronegativity increases, we increase in ionic character, decrease in covalent character. This is a nice graphic. This is just another communication of what the first one just showed. But whenever we have a transfer of electrons, we have a full positive charge and a full negative charge. Where if we have an imbalance, wherever the electrons are hanging out more, that's where we assign. The more electronegative gets the assignment of the partial negative. The other gets the assignment of the partial positive. Where we have small electronegativity differences, they're going to be about equal strength to share electrons. So there's no assignment of any partial charges. There's no unequal distribution. We say that it is non-polar.